Hello students, welcome to the class Machine Learning. So in the last lecture we have seen how to construct model for SVM for linearly separable data. Today we are going to discuss how to construct model for non-linearly separable data. So looking at this scatter plot of data having two features x1, x2. So these two classes are non-linearly separable. Means you cannot separate with line, but if there is a curve, we can separate. So how to do that? So that can be done with two ways, like using soft margin, and second way using non-linear SVM. So we are going to discuss non-linear SVM now. This is a common concept that if you transform the data set into higher dimension, the non-separable data may be separable. For example, you have two classes separate here, scatter plot. It is separated by model like ellipse. Here you have two dimensions, x1 and x2. If you transform this 2D data into 3D data, Z1, Z2, Z3, where Z1 is equal to x1 square, and let us say Z2 is your x2 square from here, and one more dimension is added, Z3, that is let us say 2 into x1, x2. Now if you transform all the data points into 3 dimensions and plot, you will find that this is separated by like plane. The data becomes separated. So as an exercise, you try to do that. You take XOR gate. In XOR gate, you have x1, x2, y. So 1, 1, 0. In place of 0, you use -1 as symmetric variable. 1 minus 1 minus, that is 1. -1, 1, 1. And -1, -1, again -1. So if -1 you consider as class 1, so class 1 may be this one and last one, and 1, 1 is class 2, and if you plot here 1, 1, -1, -1. So 1, 1 it is class 1, and -1, -1 also class 1. 1 minus 1 is class 2, and -1, 1 is class 2. Now this example, okay, you cannot separate by a line. Like if you draw a line like this, okay, same class belong to both sides. If you put your model like this, same class belong to both sides. If you put like this, same class belong to both sides. So there is no line which can separate two classes here. Okay, so what to do in this case? Okay, so we have to find out some non-linear model. So what you do, you as an exercise try to make it x1 square, x2 square, and 2 into x1, x2. So this you consider as z1, z2, z3, 3 variable, and y will be as it is, and try to transform and plot it and see how it can be separable. Okay. So the concept of kernel is, Okay, the kernel function transforms the data into higher dimensional feature space to make it possible to perform linear separation. This is another example of same. You try to, this is x1, this is x2, this is z1. z1 is equal to x1 minus 2ax1. This is z2 is equal to x2 square minus 2, some constant a. In a is here, the center a into b, the center, and a is, let us say, radius of this circle, x2, x1 square. Before doing this, you try to normalize the data between -1 to 1. Okay, normalize the data, then you transform like this, then you will find that this can be separated by a line. Fine. So what are different kernels which transform data into higher dimensional space? So this quantity we shall tell the kernel. Where this quantity came from, if you recall, in the optimization of SVM, there was a Lagrangian equation, W of alpha. It was summation of alpha I minus half of alpha I alpha j yi yj and xi transpose xj. This equation was there. So it has come from this quantity. So xi transpose xj, this will be treated as kernel. So currently here it is a linear kernel. It is called linear. But once data is non-separable, we shall transform it into polynomial kernel. So in order to make it polynomial kernel, we shall replace x with phi x. Replace x with phi x. Okay. So one of the polynomial kernel is defined like this: 1 plus xj transpose xi transpose xj whole square. Now if you make whole square and simplify, then see, currently the tuple of the data set, any tuple of the data set having two columns means two features. But after applying the polynomial, we shall see that the transformed feature having 6 dimensions. Currently it is 2-dimensional. And after transformation, we shall find out that it is 6-dimensional. How? So let us explore this quantity. Okay. Now xi is because xi is a vector of 2 values, xj is also a vector of 2 values. So xi would be xi1, okay, xi2 transpose, and xj would be xj1 and xj2. If you multiply one over one column, you will get this quantity. Now expand it based upon the formula a plus b plus c whole square. So a square plus b square plus 2ab plus b square 2ca, like that. So you will get total 6 components. Now these 6 components you split into 2 parts. Okay. each component split into two parts like 1. So I'll write 1 into 1. Okay, xi1 square, xj1 square, this component we shall keep here, and this component we shall keep to other vector. Similarly, here the I part, all the I part we shall keep here. 2 again will be split into two parts, root 2 into root 2. So one of the root 2 will come in this vector, one root 2 will go in this vector, like that. So every term is split into two parts. So now you can say that this is phi xi transpose and this is phi j. Okay. So our phi x is just ignore ij. So we get 6 terms: 1 x1 square root x1 x2 x2 square root 2 x1 root 2 x2. So finally the 2D data set is transformed into 6 dimensions using this polynomial kernel. So in the last formulation of SVM, only in the final equation here we shall replace x transpose x with this quantity. Okay, and this way our non-linearly separable data will be easily transformed as linearly separable. So there are many examples of kernel function, like this is linear function, what already we have used in the SVM modulus formulation. The next one is polynomial kernel. Polynomial kernel, as of now, last slide we have seen p is equal to 2 whole square, but it may be higher degree also. Another another kernel is Gaussian kernel, okay, or similarly sigmoid kernel, like that. Okay. So in the same formulation of xi transpose xj, at this place we shall replace okay, whatever kernel you are using. Okay. I mean there is no much change in the same formulation. At the last moment you replace this quantity of the Lagrangian equation with this kernel function. Okay. So finally, as summary, you can see in this equation in xi transpose xj, the kernel function is substituted, and as we have seen, our function of prediction was alpha I yi into xi. Okay, this is w into x plus b. So this quantity is w, and you have put here x plus b. Same can be replaced as, okay, here xi transpose x, you replace with kernel of xi comma x. This way you can solve the non-linearly separable problem. Fine. There are some properties of SVM, like it is very flexible in choosing the similarity function. Sparseness of the solution when dealing with the large data set, because only the support vector will participate. So, the other data sets are simply ignored. So it can handle the large feature space also. The overfitting can be controlled by soft margin approach, although this I have not discussed in this session. Okay, we have simple convex optimization problem. Okay, to solve it easily. There are some weaknesses like SVM is very sensitive toward noise. Okay. It only considers two classes at a time. For multiple classes, you have to build many pair of classes, pair of model. So that may be a weakness of SVM. There are so many applications you can check it. If you want to take one application like text categorization or document classification using SVM, so this you can try for. So having a set of documents, first you remove all the stop words, punctuations, and apply word stemming. Then you convert that given data set as documental matrix. After that you normalize those values in term document matrix in order to get inverse documental matrix. Now every row of the data set you may consider as phi x. Okay, apply the linear kernel or polynomial kernel and then apply SVM. There are some references and additional contents to go through that you can check it. So thank you.